video for our chapter 10 complex number. Currently on the screen is the bottom half of page 2 in the notes. Now we'll learn conjugate of a complex number. This is a very simple concept. Whenever we are given a complex number written in the form x plus yi, where x and y are real numbers, then the conjugate of z, denoted by z star. By the way, in the handwritten form, I will suggest you to write your star this way. I will suggest you to write your star like start with a vertical line followed by a cross. Yeah, and so this will be, I think, a neat way to write the star. And also when you write the letter Z, I will suggest you to write a short horizontal line in the middle here, and so that you don't get confused between 2 and Z, the number 2 and the Z. And so when you write the Z, I will suggest you to write a short horizontal line through the Z to differentiate between 2 and Z. All right, so here, conjugate of Z denoted by Z star is defined as Z star equals to x minus yi. Okay, so some quick examples here. If your Z is 3 plus 4i, then your Z star will be 3 minus 4i. You just have to reverse the coefficient of I. Reverse the sign for the coefficient of I. Okay, so in this box here, it says the conjugate of a complex number Z, it has the same real part as Z. Okay, so the real part remains unchanged, but the imaginary part, or in other words, the coefficient of I, will have now the opposite sign. The real part would always remain unchanged. I give another example. If Z is given as negative 2 plus 3i, then Z star will be negative 2 minus 3i. We only reverse the plus or minus sign of the term that contains I. The real part, the negative 2, the real part here remains unchanged. But there's also an interesting observation here. If the complex number itself has a zero imaginary part, for example, Z is just the real number 3, which can be interpreted as 3 plus 0i. Then Z star, it will be 3 minus 0i, which happen to be the same as 3. And so this tells us that if the number is itself a real number, then it will remain unchanged. And so if Z is real, then Z will be the same as Z star. And because plus 0i, when it changes to become minus 0i, it is the same as having nothing changed. And so this is one interesting observation. A real number will remain unchanged when you apply star to it. But if you refer to some online resources or some other books, there's an alternative notation for conjugate. If Z is 3 plus 2i, then Z bar is 3 minus 2i. But Z bar is just an alternative notation for Z star. But in our syllabus, it will stick to using star. If you refer to online resources, when you see a bar, a horizontal line above the Z, it means the same as star. Now let's do exercise 2, some very quick practice on finding the conjugates. Write down the conjugate of each of these complex numbers. And now when we present our answer, there are two ways to present it. So conjugate, to express the idea of conjugate, we'll use the star notation. And so the conjugate of 2 minus 3i can be written as 2 minus 3i holding bracket with a star outside it. And so this will be the conjugate of 2 minus 3i, and it will be 2 plus 3i. And so this is one way to present your answer. Another way to present your answer is to introduce the notation Z to represent the original. So if you let Z to be 2 minus 3i, then Z star will be 2 plus 3i. So you have two ways to present your answer, either in red or in purple. So to write down the conjugate is very easy. And the real part, in this case, the number 2 would remain unchanged. while the imaginary part will have the sign reversed, and -3 becomes a +3 for the coefficient of I. Okay. Now let's do part B. Okay, so if I let z to be -3 plus 4i, then my z star will be the same -3, but my 4i becomes -4i, and that's it. For part C, if I let z to be 1 minus I sub 3, I choose to rewrite it as 1 minus sub 3i, so that it's clearer that the coefficient of I is minus sub 3. Then my z star must be 1 plus sub 3i. Okay, done. Okay, where the minus gets reversed to a plus. Okay, this minus gets reversed to a plus, while the real part of 1 remains unchanged. Okay, then for part D, if I let z to be 2i, which can be interpreted as 0 plus 2i, then my z star must be 0 minus 2i, which is simply just minus 2i. And notice that the real part of 0 is unchanged, while my plus 2 as the coefficient of I, it has a sign reversed to become minus 2. Okay, of course, when we are already familiar, of course, you can write if you let z to be 2i, then z star is simply minus 2i. It's not a must to write out the 0 in front of the 2i. Then part E. Part E is, I will let z be the given number 1/2 3 minus I sub 2. And to make it easier to see, I will just distribute my 1/2 into the bracket so that I have 3 over 2 minus 2 over 2 as the coefficient of I. And then z star is 3 over 2 plus 2 over 2i, where the minus reversed to become a plus. One interesting observation here is that if we factor back out the 1/2, I can write this as 1/2 times 3 plus I sub 2. And so notice that 1/2 actually remains unchanged. If you compare with the original question, the 1/2 remains unchanged. And the 3 plus I sub 2 is actually the conjugate of 3 minus I sub 2. And so this shows us that from this question, we observe that if you have a real number coefficient, let's say for k being a real number, if we have kz with a star applied to it, it's the same as k times z star, where the real number coefficient of k, it remains unaffected. K is a real number coefficient for the complex number z. And so when the star is applied to it, the k remains unaffected. And so just one interesting observation here. Okay, now let's move to part F. Let z to be minus 5i, then z star must be positive 5i. That's it. Yeah, the reason why it becomes positive 5i is because this number negative 5i can be written as 0 minus 5i. So when you take the conjugate, it becomes 0 plus 5i. Where the real part of 0 is unaffected, and the coefficient of I being negative 5 gets reversed to plus 5. Okay, now we'll move to the next page, number 3. Properties of conjugate pair. Property A is especially important in our syllabus. So when we have a pair of conjugates Z and Z star, there are a few interesting observations when we multiply the pair, when we add up the pair, and when we subtract the pair. Right. So part A is to study what happens when we multiply a conjugate pair. And so if z is x plus yi, then z star must be x minus yi. So then what is z times z star? It becomes x plus yi multiplied by x minus yi. Okay, recall from your elementary algebra that if you have a plus b times a minus b, you have a squared minus b squared. Okay, now, if we treat x as a, and b as yi, if you treat a as x, if you treat a as x and b as yi, then we have the form a squared minus b squared here in our expansion. So that would be x squared minus b is yi whole thing squared. Well, x squared is simply just x squared. Well, yi squared, the square can be distributed over the product. So you have y squared, I squared. Y squared, I squared. Recall that I squared is defined as -1, and we learned this on page number 1. So I squared, I'm going to replace it by 1. Sorry, by -1. Okay, so eventually I get x squared plus y squared. So this is a very important result. And later in this chapter, when we do computations involving multiplication of a conjugate pair, we will use this result as a shortcut. Okay, so what does this tell us? It's telling us that, for example, if I have 3 plus 4i times 3 minus 4i, this is a pair of conjugates, obviously, being multiplied together. And so without going through the process of writing 3 squared minus 4i whole thing squared, and you get 9 minus 16i squared, 9 plus 16, 25. Without going through the entire process, if you know that when you multiply z and z star, you simply get x squared plus y squared, then here we can actually jump to, because this is x plus yi times x minus yi, you can straight away get x squared plus y squared, where your x is 3 and y is 4. So that means your 3 plus 4i times 3 minus 4i, you can write out the result straight away as 3 squared plus 4 squared, where your 3 is x and 4 is y, and you straight away get a 25. And so that can save you a bit of time. And we will frequently encounter such multiplication later in this chapter. Okay, so you should remember this result. Okay. When you have a pair of conjugates multiplied together, okay, you simply get x squared plus y squared, where x is the real part and y is the imaginary part. So, some people may wonder, can I take my y to be -4? Okay, like if you have 3 minus 4i times 3 plus 4i, I can regard this as z and this to be z star. Okay, there's nothing wrong, because they are still a pair of conjugates. And in such a case, my x will be 3 and my y will be -4. Okay, so you take 3 squared plus -4 squared, it will still give you the same answer of 25 at the end. Okay, so it doesn't really matter whether if you take y to be -4 or if you take y to be a +4. It won't affect the final answer. So it doesn't matter whether you take -4 or +4 as the y. Right. So let's read through some remark down there. Right, point number 1 says the product of a conjugate pair, when you have z times z star, you always get a real number. It is always a real number. Okay, this property is very useful in simplifying expressions with complex number at the denominator. Okay, so in page number 5, we will learn how to divide complex numbers. And so when you have complex number at the bottom of a fraction, multiplying the bottom of the fraction by the conjugate is a very common technique to get rid of I from the bottom of the fraction. We'll do that on page 5. And so This is a very important observation here. When you multiply z and z star, you get x squared plus y squared, which is real. A real number means it doesn't contain any I. Doesn't contain I. Okay, so this is a very important property. Okay, so multiplying a complex number by its conjugate is a common technique for us to get rid of I. And so in the example written in red on the right of your screen, you can see that when we have 3 plus 4i times 3 minus 4i, our final answer is simply just 25, okay, where our 25 doesn't contain I at all. Okay. Part 2 says, when multiplying a conjugate pair, we only need to take the real part squared plus the imaginary part squared. And so again, referring back to the example in red color, you just need to take 3 squared plus 4 squared. It's just the real part of 3 squared plus with the imaginary part of 4 squared, and you straight away get the result. And so you can memorize this result, and you are strongly encouraged to memorize this result. And here I say remembering this can save you time when performing computations. Okay. Part 3 says the modulus of a complex number, the notation modulus z, will be introduced in detail on page 13 of this tutorial. And so when you have modulus of a complex number, for example, modulus of 3 plus 4i, the modulus here has a different meaning. It is unlike modulus of a real number. When you have modulus of -3, you simply get a 3. When you have modulus of 4, you get a 4. That is for modulus of real number. But when you have modulus of a complex number, it has a different meaning. Okay, so we'll cover that in detail on page 13 of this tutorial. Okay, now I'll just quickly flip to page 13 to show you. Yeah, so modulus of z is actually the length of the vector connecting origin to the point representation of the complex number in the Argand diagram. And we'll cover more of this later in this chapter. And so for now, you just accept that for a complex number z equals x plus yi, modulus z can be calculated as square root of x squared plus y squared. And for now, we'll just accept this. Later, we'll learn this in detail. Right, so for example, modulus of 3 plus 4i, where your x is 3 and y is 4. X is 3, y is 4. And this is just square root of 3 squared plus 4 squared, and you get a 5. And so this is how z is computed. I mean, modulus of z is computed. So that also means that the x squared plus y squared that we had just now, I can actually continue on further and write this as square root of x squared plus y squared with a square at the outside, so that when my square root and the square at the outside cancels, it still remains the same thing. But I know square root of x squared plus y squared is how we compute modulus of z, and the power 2 is at the outside. So this actually proves the result at the top of your screen, where your z star is equals to x squared plus y squared, which is also equals to modulus of z squared. And so at this stage, it will just accept that modulus z is computed using square root of x squared plus y squared. Later in this chapter, it will learn it in more detail. Now let's move to part B on page 3. For part B, you do not need to memorize this result. This is not as important as the result in part A. Part A is very important. This one, you have to memorize the result. But for part B, it is less important. And this is just for you to be aware that when you add up a pair of conjugates, don't be surprised if you get a real number, because it's a guarantee that you will get a real number. And so the proof is easy. If your z is x plus yi, your z star will be x minus yi, so that your z plus with z star will be x plus yi plus with x minus yi, where your plus yi and minus yi will cancel, giving you just a 2x. But what is x? X is simply the real part of z. So This shows us that when we take the sum of a conjugate pair, when we add z by z star, it is a guarantee that we get a real number. A real number means a number that doesn't contain I. Doesn't contain I. So just one quick example. If my z is 3 plus 4i, my z star is 3 minus 4i, then it's obvious that z plus z star would give you just a 3 plus 3, which is 6. And this number doesn't contain I. So this result you don't really have to memorize, because just by performing that addition very quickly, you will be able to realize that your answer actually doesn't contain I. And so just for you to know, when you add up a pair of conjugates, you always get a real number. So don't be surprised if you see that the I disappears when you add up a conjugate pair. Next, when you subtract a conjugate pair, when you take z minus z star, you will get a purely imaginary number, a number that only has the imaginary term, a complex number without the real term. So the proof is also very easy. If your z is x plus yi, then your z star must be x minus yi. So your z minus z star must be x plus yi minus x minus yi. When you expand this, you get x plus yi minus x plus yi. Plus x and minus x will cancel. That gives you a 2yi. And what is y? Y is the imaginary part of z. So I have 2in bracket z, whole thing multiplied by I. 2y times I. Right. So imaginary part of z, or the y itself, is simply a real number. So 2y is just a real number. Some real number times with I, it is a purely imaginary term. Earlier on page 1, we already learned what purely imaginary means. So it is just some real number times I. So the note at the bottom here says, when you take the difference of a conjugate pair, when you take z minus by z star, you get a purely imaginary number, where it only has the term that contains I. It doesn't have the real term. It doesn't have the real term without I. So one quick example, if I have z being 3 plus 4i and my z star being 3 minus 4i, so z minus z star is obvious that you have 4i plus with 4i, and that gives you an 8i, where this is a purely imaginary term. Okay. Next, moving to page number 4. Property D tells us that when you have z star and you take the conjugate of it, z star with a star at the outside, in other words, conjugate of a conjugate. So the note here says conjugate of the complex number z is z itself. In other words, when you have double star, the double star will just cancel. And this one is also very easy to prove. So if you let z to be x plus yi, then z star would be z x minus yi. So your z star with a star is just x minus yi with a star. And because here I'm just putting in x minus yi to replace my z star. Okay, now my x minus yi, when I apply star on it, the real part z remains unchanged, but this term negative yi should reverse the sign to become plus yi. And what is x plus yi? It becomes z. So the overall effect is z star with a star just give me a z. Z star with a star just gives me a Z. It's a double star means they cancel each other. The two stars will cancel. Okay, next, other properties. So if Z is a real number, then Z star will be equal to Z. So this one we have already briefly mentioned it when we did bottom part of page 2. Okay, so for example, if Z is the real number of -2, which is the same as -2 plus 0i, then Z star will be just -2 minus 0i, which is the same as -2 itself. But what is -2? -2 is just the original Z. And so that means a real number is unaffected by the star. So this means a real number is unaffected by the conjugate operator star. Okay. Property F and G and H and J. Okay, so these are very useful properties for the conjugate operator star. Okay, property F says the star operator can be distributed over addition. Okay, so when you have two complex numbers added up, then the whole thing you take the star. You can distribute your star over the addition. Okay, so this is very useful. Right. Then for property G, it says the star can also be distributed over subtraction. Property H says the star can be distributed over multiplication. Property J says the star can be distributed over division. And so the star operator, it has this very convenient property that allows us to distribute the star over addition, subtraction, multiplication, and division. Okay, so we can confidently distribute the star over plus, minus, multiply, or divide. Okay. Property I says, okay, if you have z square, then you take the conjugate of it. The conjugate of z square is the same as z star followed by the 2. Okay, so in other words, the power and the star, you can interchange the position. Whether you square first, then only you take the conjugate, or you take the conjugate first, then only you take the square, it will be the same. So this is also a convenient property that the conjugate operator has. And in fact, in general, for any positive integer n, z to the power of n with a star is the same as z star to the power n. And so the star and n can interchange position easily. And we are confident that this will be correct because it's a property of the conjugate operator. But however, such properties are not very commonly used in the exam question, just for you to know. Okay. Okay, so out of so many properties of conjugate that we have learned so far, what are those which are commonly used? Okay. The one that is very commonly used, the most commonly used property of conjugate is property A, where you take z multiplied by z star, you will get x squared plus y squared. This one is used very frequently. Property A, I would say, is the most important property in our syllabus for regarding conjugate pairs. Property B and C are not so important. This is just for you to realize that when you add up a conjugate pair, you get a real number. When you subtract a conjugate pair, you get a purely imaginary number. Property D, this one is sometimes useful when solving an exam question. When you have a Z star and you apply another star to it, the double star will just cancel. And the other properties from E to H, you can just read through. I would say this is not so frequently used, but it's good for you to know that the star can be distributed safely over addition, subtraction, multiplication, and division. Next, on arithmetic operation. Okay, so addition and subtraction will be very easy for a complex number, because the way it works is just like our elementary algebra. Nothing special about it. So when you have two complex numbers being added up, where z is x plus yi and w is u plus vi, where x, y, u, and v are all real number coefficients, then the way we do addition and subtraction is just like normal algebra. Okay, so in this example, example number one, when you have two complex numbers being added up, the brackets can just be removed, because it's a plus here. So it doesn't affect anything when you remove the brackets. 3 plus 4i plus 5 plus 6i. So what we'll do is just like usual algebra, where the term without I can be added together. 3 plus 5 becomes 8. 4 plus 6 becomes 10. And that's it, done. Just like our usual algebra, and nothing special about it. Next is subtraction. So when you remove the brackets here, this negative you have to be more careful, because it will be distributed over the two terms 8 and 2i. 5 plus 3i minus 8 minus 2i. And then the terms without I, we just compute them. 5 minus 8 will give us a negative 3. Plus 3i minus 2i, that gives you a plus 1i, and that's it, done. Okay. Next, on multiplication. Okay, multiplication of complex number, it works in a similar way, just like your usual algebra, where you just expand the bracket. Just expand the bracket. It's just like how you would expand a plus b times c plus d. So you would get AC, AD, AC plus AD followed by BC plus BD. It's just a usual expansion. However, one thing to notice here is that when you have I to the power of 2, you are always expected to simplify it using the fact that I squared is negative 1. Whenever we have I power 2, we are always expected to simplify it by replacing I squared by minus 1. Okay. So look at the combinations that we will get when we expand these two brackets. Okay. So there are two combinations that will generate the real term at the end. 3 times 1 will generate a real term. 4i times minus 2i, this will also eventually become a real term. Because 4i times minus 2i, that will give us a minus 8i squared. But I squared is negative 1. That becomes a positive 8 eventually. And so it's actually these two combinations, the 3 times 1 and the 4i times minus 2i, that will generate real terms at the end. A real term means the term that don't contain I. Right? So the 4i times negative 2i, it eventually becomes a number that doesn't contain I. And so these two combinations, which I color in green here, they are the combinations that generate real terms. So what are the combinations that generate the imaginary terms? Those will be this and this, the inner and outer combination. Right, so when doing such expansions, and to save you a bit of time, I will suggest you to write down the real term together and imaginary term together. Okay. So the first green combination gives me a 3. The second combination will give me minus 8i squared. Okay, I will write these two together, followed by the two red color combination. In the outer combination, I have a minus 6i. Inner combination, 4i times 1, I will have a plus 4i. So that eventually I get the green color bracket. It becomes 3 plus 8. You can be a bit faster. I squared is negative 1. So minus 8 times minus 1 gives you a plus 8. You are allowed to be a bit faster. 3 plus 8 here, and I have plus with the red term, that will be a negative 2i. so that eventually we get 11 minus 2y. And that's it. So this is how I suggest you to do multiplication of complex numbers. You multiply the real terms, group them together, then followed by the imaginary terms, group them together. So this can save you a bit of time of rearranging terms. Now let's do a few more examples. Property 2, example 2. Okay, when you have a complex number with a power 2, recall from your elementary algebra that you have a plus b power 2 that gives you a squared plus 2ab plus b squared, which can also be rearranged as a squared plus b squared plus 2ab. Okay, when doing expansion of complex number, I will suggest you to write your expansion in this form. Okay, now why do I suggest you to write a squared plus b squared and 2ab as the last term? It's because these two terms, the a squared plus b squared term, are actually the term that will eventually become real. Okay. So in this case, you have your 3 squared plus with negative 4i squared plus with 2 times 3 times minus 4i. Okay. But the first two terms will eventually become the real term. 3 squared is 9 minus 4i whole thing squared. When I have negative and square, the negative will just disappear. Okay. So I end up having plus 16i squared. And the last term is 2, 3, 4 is 24. That's negative 24i. I squared is negative 1. So now I have 9 minus 16. Plus 16i squared becomes minus 16 because I squared is negative 1. And negative 24i remains. This becomes minus 7 minus 24i. And that's the final answer. So this is so when you have a complex number to the power of 2, I will suggest you to write the first term squared plus the second term squared first, then only the 2ab term. It will be more convenient to do it this way. And so that you already have your real terms grouped together at the front. Okay, and the third one, 3 minus 4i times 3 plus 4i. Okay, this is product of a conjugate pair. And 3 minus 4i and 3 plus 4i, they are obviously a conjugate pair because the real term 3 is the same. The imaginary term have opposite sides. So this is product of a conjugate pair. So if you remember the result that we have just learned moments ago, when you have z times z star, the result is simply x squared plus y squared. Here you can just apply that result. So you just take the real part, which is 3, you square it. The imaginary part, whether you take negative 4 or plus 4, it doesn't really matter. It doesn't affect the final answer. So I'll just take 4 squared and you get 25. That's it. Next, we'll move on to division. Okay, so this part says to divide a number by a complex number, the denominator has to be transformed to a real number. Okay, so it's saying that whenever you have some expression that contains some I at the bottom of the fraction, our syllabus expects us to get rid of I from the bottom. If such a number is our final answer, it cannot be left that way. Such a number cannot be left as a final answer. Our syllabus expects us to get rid of I from the bottom of the fraction. Okay. So how do we get rid of I from the bottom? Is by multiplying the top and bottom by the conjugate of the bottom. Multiply the top and bottom by the conjugate of the bottom. And why do we want to multiply by conjugate? Because we know when we multiply a conjugate pair, we end up getting a real number as the result. So we'll copy back this original fraction. We'll multiply by 2 minus 3i, 2 minus 3i, where 2 minus 3i is the conjugate of 2 plus 3i. Okay, so that when the two numbers at the bottom gets multiplied together, we have the form x plus yi times x minus yi, which will give us x squared plus y squared at the bottom. Okay, so I'll do it a bit slower this time. I have 3 times 2 minus 3i at the top, 2 plus 3i times 2 minus 3i at the bottom. Okay, at the top, I can just expand to become 6 minus 9i. At the bottom, I have a conjugate pair. Okay, this is a product of conjugate pair, where I know the result must be x squared plus y squared. So x is 2, y is 3. So I have a single 13 at the bottom. And it's common for people to write as two separate terms, 6 over 13 minus 9 over 13i. And that. For complex number, it is common for people to write in the form of x plus yi at the end. Okay, now let's move to part 2. Okay, I mean the second example. Okay. Okay, 2 plus I divided by 3 minus 2i. Okay, so our aim is to get rid of I from the bottom. So I copy this original question first. I have to multiply by the same number at the top and bottom, and that number will be the conjugate of the bottom, 3 plus 2i. Remember that the conjugate of a complex number always has the same real part. The 3 remains unchanged, while the imaginary term, minus 2i, we have the sign reversed to become plus 2i. Okay, so at the top now we have a product of two complex numbers, which we'll have to expand later. At the bottom is 3 minus 2i times 3 plus 2i. Okay, the bottom is a product of a conjugate pair again, which we know will have the form x squared plus y squared, where x is the real term and y is the imaginary part or the coefficient of I. So I just take 2 squared. Okay, whether you take negative 2 squared or 2 squared, it doesn't affect the final result. So it doesn't matter. Okay. At the top, at the numerator, I'm going to expand it using the suggested method, where I will take 2 times 3 and also I times 2i. I'll write these two combinations first. So that gives me a 6 plus with 2i squared. These two terms will eventually generate the real term. Okay, then next, I will write down the other two combinations, which generate the imaginary terms. Okay, so the outer combination will give me a 4i. Inner combination is a 3i. And I extend my line longer. Right, so the red colored terms will become 6 minus 2 because I squared is negative 1. Because I squared is negative 1. Right, then the purple colored terms will be just 7i. And the bottom, I have 9 plus 4, which is 13. So I have a 4 plus 7i divided by 13, which if written as separate terms, I have 4 over 13 plus 7 over 13i. Okay, done. Okay, next we'll move to page number 6 on how to simplify higher integer powers of I. Okay. But in our syllabus, sometimes you might encounter higher integer powers of I, possibly I power 4, I power 5, I power 6. Okay. So how can we simplify such expressions very quickly? So let's study the pattern first. So obviously, I to the power of 1 must be just I, lah. Nothing much to talk about it. Okay, I squared, by definition, we know is -1. I cubed, it can be written as I squared times I, right? So I squared is -1. So -1 times I. It becomes -I. Okay, so I cubed is -I. Okay, then what is I power 4? I power 4, I can interpret it as I squared, which is -1 times -1. -1 times -1 is just a +1. And so I power 4 being +1 is a very important and useful result that you need to notice. Okay, so that means that I power 5 can then be easily simplified by writing it as I power 4 times I. Okay, where I know I power 4 is 1. Okay, so it's simply 1I and it's just I. I power 6 is I power 4, I power 2. Okay, where I power 4 is 1 and I power 2, I just write it that way. And I power 2, I know from the first column of this table that it is -1. I power 7 is just I4, I3. That is just 1 I power 3. I power 3, I know is -I from the column on the left. I power 8 is just I4, I4. And it's just 1 times 1. And it's just 1. And now let's look at column 3. I mean, I power 9 until I power 12. Yeah, I power 9, I can extract out I power 4, I power 4, and I power 1. Okay, I power 4 becomes 1. Both of I power 4 becomes 1, so it's just I. I power 10, I can extract I power 8 again, leaving me with I squared. Okay, both the I power 4 will become 1. So I'm left with just I squared, and I know I squared is -1. I power 11 is I power 4, I power 4, I power 3. That leaves me with I power 3, and I know I power 3 is minus I from the first column. I power 12 is I4, 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 and everything is 1, so it's 1. Okay. So looking at the 3 columns, what can we observe? Now, the first thing that is quite obvious to most people is that when you have power of I which is higher than 4, the way to simplify it is just to extract as many I power 4 as you can. And using the fact that I power 4 is equal to 1, and then the thing becomes very simple. For example, if you have I to the power of 201, you can just extract I power 4, I power 4, I power 4 as many times as you can. Now, how many I power 4 can we extract out? It will be 50 times. Because 4 times 50 will give you 200 as a power. So that leaves you with I power 1. Because all the I power 4 are all just 1, 1 multiplied by itself, no matter how many times, will be still 1. So we simply get I power 1, which is just I. So this is one important observation from the table. When you have any power of I which is higher than 4, you can always simplify it by extracting as many I power 4 as you can. But a neater way to write this will be writing it as I power 4 to the power of 50 multiplied by I. Yeah, this would be a neater way to write, and it becomes 1 power 50 times I, and it just becomes I. Yeah. Okay. Another thing to observe is that, okay, let's look at row by row. Okay. I power 1, I power 5, I power 9, they are all equal to I. So you can also expect, in looking at the pattern, you would expect I power 13 to be also equal to I. if you add the power by another 4, I power 17 is also I power 21 would be also I. Then if you look at the second row, you have power 2, power 6, power 10, all of which equals to -1. So you would expect I power 14 to be -1, I power 18 to be -1, I power 22 to be -1, and so on. If you look at the third row, I cube is minus I power 7 also the same, I power 11 also the same. That means you would expect I 15 to be -1, I power 19 to be minus I, and I power 23 to be minus I. And the last one, I power 4, I power 8, I power 12, those are all 1. So you expect I 16 to be 1, I 20 to be 1, I power 24 to be 1. Okay, so from here, we can write down a general result. Okay, for non-negative integers, n, we observe that I to the power of 4n plus 1 is always equal to I to the power of 4n plus 2 is always equals to -1, I to the power of 4n plus 3 is always -I, and I to the 4n is equals to 1. So this is a result that is applicable for all non-negative integers n. Okay. There's also another way to uh, interpret the result that we have here. Okay. So you notice that as we increase the power of I 1 by 1, the answer that we get, it will be I followed by -1 followed by -I followed by 1. And when you increase I by another power 1, when you have I4 going to I power 5, the cycle actually repeats. So you again have I -1 minus I1. Looking at the third column, it's again I -1 minus I1. And so you actually have a cycle. I -1 minus I1. It's a cycle. So you have this cycle. When you keep increasing the power of I1 by 1, you have this this cycle result here. Okay. Now with all those in mind, let's try to simplify I power 84, I power 203, and so on. These few examples. Okay. I to the power of 84. So from our experience, we know that we will try to factor out as many I power 4 as we can. So from your calculator, you notice that 84 divided by 4, it nicely gives you a 21. Yeah, it gives you 21. So that means that this can be written as I to the power of 4 multiplied by itself for 21 times. So this is just 1 to the power of 21, and that gives 1. That's all. I203. I power 203, it is I to the power of 4 multiplied by itself 50 times. So that would have I power 200 already. Then you have to multiply by I power 3. Okay, so you have now 1 power 50 times I cube. The I cube, if you memorize the result, it is -I. If you do not memorize, also don't worry. You can write it as I squared I. So it becomes 1 power 50 will disappear. This becomes just a 1. I squared I becomes a -1I. So it's -I. I power 98. Okay. So if you find it hard to figure out how many I power 4 that we can factor out, then you can always use a calculator to press out what is 98 divided by 4. 98 divided by 4 is 24.5. Actually, you take the integer part of it. That means that there are 24 repetitions of I power 4 that you can factor out. So you have I power 4 to the power of 24. If 4 times 24 using a calculator will give you 96. So that leaves you with I squared. So this is 1 to the power of 24, while I squared becomes minus 1, and it becomes just minus 1. Last one, I power 79. So again, using a calculator to check, 79 divided by 4, that gives you 19.75. So that means there are 19 repetitions of I power 4 that you can factor out. 4 times 19 will give you 76 as the power of I. So you need 3 more. So you have 1 to the power of 19. I cubed is I squared I. So you have negative I at the end. Okay, next. How about negative integer powers of I? If you have negative integer powers of I, it can also be simplified in a somewhat similar manner. Okay. So I to the power of negative 1. Right, first of all, I to the power of negative 1, just like the usual 2 to the power of negative 1 is just 1 over 2. So similarly, I to the power of negative 1 is 1 over I. Okay. Now, what happens if I multiply top and bottom by I? I have 1 over I times I over I. So that gives me I over I squared, and I know I squared is negative 1, so that gives me negative I eventually. And so I power negative 1 would give me a negative I. Okay, so next, what is I to the power of negative 84? Okay, so one suggested method for you to deal with it is you would try to write negative 84. You would try to write negative 84 as uh, 4 times something plus something. You will try to write negative 84 as 4 times something plus something. And this number, you want it to be positive. You want it to be positive for your own convenience. Okay. So negative 84, it can be written as 4 times minus 21. You can written as 4 times minus 21. Okay, which means I can now write, by law of indices, I can write it. By law of indices, you know that x to the power of mn is the same as x to the power of n times, with a power n at the outside. So here I can write as I power 4 with the power of negative 21. So it's just 1 to the power of minus 21. And 1 to the power of anything, including negative power, 1 to the power of negative 21, well, it's just 1 over 1 power 21, which you know is just 1. 1 to the power of anything, even if that power is a negative integer, it is still 1. Because 1 power minus 21 is simply 1 over 1 power 21 is just 1. Right. Next, I power negative 203. Okay, so for this one, I will first interpret it as I power minus 204 plus 1. Next, okay, so why do I want to write as negative 204 plus 1? It's because I know negative 204 is a multiple of 4. And then some people may wonder, why don't I write I negative 200 minus 3? But this is also correct, of course, but it's not convenient for me because later I will end up having I power negative 3, which is not as easy to deal with uh, as compared to I power 1. And like it will be easy to deal with if you end up at the end, you end up having I power 1, I power 2, and I power 3. It will be easier to deal with as compared to I power minus 1, I power minus 2, and I power minus 3. Having positive power at the end will be easier to deal with. Right? That's why I prefer to write minus 203 as minus 204 plus 1. But now the minus 204 can be written as a multiple of 4. I mean, I can write as 4 times negative 51 plus 1. So by law of indices, I can write this as I to the 4 to the power of minus 51 at the outside, followed by I power 1. This is just 1 to the power of negative 51 times with I, and it's simply just I. Okay, next. I to the power of minus 79. But this can be first written as I to the power of minus 80 plus 1. Minus 80 can be written as 4 times minus 20. Then by law of indices, it becomes I to the 4 power negative 20 followed by I to the 1. Then that becomes 1 to the power of minus 20 times I. So it eventually becomes just I, and that. Okay. Now we'll move to exercise 3A, where we simplify slightly more complicated expressions involving some powers of I. Simplify each of the following complex number, express it in the form a plus bi, where a and b are real. Part A, 1 minus I to the power of 2. Okay. So we'll expand it using a squared plus b squared plus 2ab. So that gives us 1 plus by I squared minus 2i. It's just a usual quadratic expansion. And I squared is negative 1. So we eventually get minus 2i as a final answer, and done. Next, part B. 1 minus I to the power of 5. I hope you can still remember binomial expansion learned in P1, chapter 8, which says if you have 1 plus x to the power of n, if n is a positive integer, then it will be 1 plus nc1x to the 1 plus nc2x to the 2, and so on, and the last one will be ncnx to the n. So we're going to use this binomial expansion formula here. Okay, so I have now 1 plus with 5c1, where the x should be taken as negative I. So that's negative I to the 1. 5c2, negative I to the 2. 5c3, negative I to the 3. Followed by 5c4, negative I to the 4. And lastly, 5c5, negative I to the 5. 5c1 is just 5. And negative I, well, just bring the negative to the front. So at minus 5i. 5c2 would be 10. Negative I holding to the power of 2, I will get positive I squared. And bearing in mind that negative, when I take an even power, that negative will be gone. Third term, negative to an odd power, so that changes the plus at the front to become a minus. 5c3 is 10 again, and I have I cubed. Next term, negative to an even power, that negative disappears. So the plus at the front remains as plus. And 5c4 is 5 and I to the 4. 5c5 is just 1 and negative to an odd power, that gives me a negative I to the 5. Then only I simplify further. I squared becomes negative 1. I cubed becomes I squared I to the 4, I memorize the result is 1. This is I4 times I. Then simplify further. 1 minus 5i, this is minus 10. I squared becomes negative 1, so that changes the negative in front to become a plus. Plus 10i. Next one is just 5, and I power 4 is just 1, so I get only an I. Okay, now it's simple enough. We can add up the real terms. 1, negative 10, and 5. I have 6 minus 10, that is a negative 4. Okay, the terms with I have minus 5 plus 10 minus 1. That gives me a 4. And done. Okay, but see, I divided by 3 minus I. Okay, so this is an expression where we have some I at the bottom. The syllabus expects us to get rid of I from the bottom. We copy the original fraction, multiply by the conjugate of the bottom. Of course, the same 3 plus I would be needed above to maintain the equality. Okay, then, now at the bottom, I have product of a conjugate pair. At the top is just I times 3 plus I. Okay. At the bottom, this is a conjugate pair being multiplied together. The result will be x squared plus y squared, where my x is 3 and my y is 1. Okay, remember that the y is the coefficient of I. So coefficient of I is either negative 1 or plus 1 here. You just simply take either one. Okay? You take either negative 1 or plus 1, it doesn't affect. So it's 1 squared. At the top, I have 3i my plus with I squared. But I squared is negative 1, so I will rewrite as 3i minus 1 divided by 10 at the bottom. Split it into two separate terms, and I rearrange it. I write the real term at the front, negative 110 plus 3 over 10 times I, and that's the answer. Okay. Lastly is part D. Two minus I divided by 2 plus I with a power 2. Yeah, expand the bottom first. So when we do such kind of quadratic expansion for complex numbers, it's advisable to write down the terms in the form a squared plus b squared plus 2ab, where you write the a squared plus b squared first. So I write 2 squared plus I squared first, followed by 4i at the back. Why do I prefer to write 2 squared plus I squared first? Because these two terms will eventually generate the real term. So it would be more convenient if we group them together right from the beginning. At the top, 2 minus I remains unchanged for now. 2 squared is 4, I squared is negative 1. 2 minus I again is unchanged. 2 minus I unchanged again, 3 plus 4i at the bottom. Okay. Now we have to get rid of the I from the bottom, and the technique is to multiply by the conjugate of the bottom, 3 minus 4i. And of course, I need the same 3 minus 4i above to maintain the equality. Now at the bottom, I have a conjugate pair being multiplied together. At the top is just a product of two complex numbers. At the bottom, product of a conjugate pair, I know the result is x squared plus y squared, where the x is 3 and the y is 4. At the top, when we do such expansions, it is advisable to expand the combinations that will generate the real term first. And so the real term will be 2 times 3 and the item times with the other item. 2 times 3 gives me a 6. Minus I times minus 4i, I have a plus 4i squared. So these are the terms that will generate the real term. Next will be to multiply the terms that generate the imaginary terms. And those will be the inner and outer combination. The outer combination gives me a negative 8i. Inner combination is a minus 3i. And now I extend my line, make it longer. Okay. Now my green colored terms will become 6 minus 4 because I squared is negative 1. My purple colored term will become a negative 11i. At the bottom, I have 25. So now it's time to split the fraction into two separate terms. I have 2 over 25 as a real term, minus 11 over 25i as an imaginary term, and done. Right, next, move on to question 2. But if z is this number, show that z4 plus 8 to the 8 times z equals to 0. But this is just a simple question. Okay. So if z is 1 plus z3i, I prefer to write the I at the back because it's easier to do computations that way. If you choose to write the I at the back, make sure to leave a bit of distance between the Z3 and the I, so that it will not be misinterpreted. Then Z4 plus 8Z will be equals to. So don't write your 0 too early, because 0 is the result that should be obtained by computation. So you expect the final answer to be 0. So don't write your 0 too early. Your 0 should not appear too early. So we want to establish this equality by starting with the left-hand side and ending with the right-hand side. Okay, so now we just sub in our z. And then just do the expansion. Okay, so this one we just apply binomial expansion. Okay, we have a leading one, and so the expansion will be quite, not as messy. Okay, so we'll use the expansion of 1 plus x to the 4, it being 1 plus 4c1x to the 1, 4c2x to the 2, and so on. Okay, where the x will be treated as Z3i. Z3i with a power 2, 4c3, Z3i to the power 3, followed by 4c4, Z3i to the power 4. Okay. Yeah, this last term I will just write down the expansion in a different color. 8 plus 8 Z3i. 4c1 is just 4, so I have 4 Z3i here. 4c2 is 6. Okay, Z3 with a square will give me just a 3, so it's just 3i squared. 4C3 is 4. Set 3 to the power 3 will give me 3 set 3, and followed by I cubed. Okay, so make sure you know how to do like square root with a certain power. So make sure you know how to expand this very quickly. Like set 3 power 3 can be interpreted as set 3 squared times with set 3. And this set 3 with a power 2 is simply just a 3. That's how I get my 3 set 3 so quickly. 4C4 is just 1, and set 3 power 4 is just 3 times 3. Set 3 power 4 is set 3 to the 2, set 3 to the 2, which is just 3 times 3. So that should give you a 9. And I to the 4, the purple colored term remain unchanged for now. Okay. The I squared becomes a negative 1, so that changes the plus in front to become a minus. 6 times 3 is 18. I have 12 set 3, I squared I. I power 4 is just 1, so it's just a 9 there. I squared is a negative 1, so that changes a plus in front to become a minus. Okay, the other term I will just copy back. Okay, now we hope to get a 0, and let's check whether we do get a 0 there. The term without I have 1 minus 18 plus 9 plus 8. Pressing a calculator, you get a 0, so that's good. And the remaining terms that contain I have 4 set 3 minus 12 set 3 plus 8 set 3. That gives me a 0 coefficient. So yeah, we do get a 0 at the end. And we have shown the equation that they asked us to show. Okay, question 2 is done, and we'll move to question 3. Question 3 is, given that z equals to this complex number, find z star. Okay, so we are given z to be 2 minus 7i, therefore z star must be 2 plus 7i. The imaginary term have the sign being reversed. Okay. So part A, z times z star is just 2 minus 7i times with 2 plus 7i. This is a product of a conjugate pair. The result is just x squared plus y squared. That's 2 squared plus 7 squared, and you get 53 straight away. Take that. Part B, 1 over z star. That is 1 over 2 plus 7i. We'll have to introduce the conjugate of 2 plus 7i, that is 2 minus 7i, to be put at the bottom, and to get rid of I from the bottom, and of course I need the same number above. Okay. Now at the bottom I have a product of a conjugate pair, which I know the result is 2 squared plus 7 squared, and at the top I simply get 2 minus 7i. Okay, splitting it, wait, I should compute the bottom as 53, 2 minus 7i on top. Splitting it into two terms, I have 2 over 53 minus 7 over 53i, and done. For part C, 1 over z, the whole thing star. Recall that on page 4 earlier, we know that the star can be distributed over division. So I can distribute my star to the one above, 1 star divided by z star. Hey, but 1 is actually a real number. So from the property E on page 4, if something is a real number, then when we apply star to it, it's unaffected. So 1 is a real number that doesn't contain any I. When we apply star to it, it remains as 1. 1 over z star. And then what is 1 over z star? It is the same as question B. And so we can just take the result from question B, 2 over 53 minus 7 over 53i, and done. So here we can just using part B. Okay. And the last one, z star over z. Z star over z. Z star is 2 plus 7i. Z is 2 minus 7i. Okay. We have to multiply by the conjugate of the bottom. So that now at the top I have 2 plus 7i multiplied by itself, which is 2 plus 7i whole thing power 2. And at the bottom I have the conjugate pair multiplied together. The bottom I know is 2 squared plus 7 squared. At the top I just expand using the usual quadratic expansion, writing a squared plus b squared plus 2ab. I have 4 plus 49i squared. And plus with 2 times 2 times 7i, that is 4 times 7i, that's 28i. 49i squared is minus 49, because I squared is negative 1. So it changes the plus in front to become a minus. Plus 28i divided by 53. This is negative 45 at the top, plus 28i divided by 53. So at the end, we have minus 45 over 53 plus 28 over 53i. And done. Right, so that's all for this video. Okay, I'll continue with page 7 in the next video.